Hi students, welcome to HSC Chemistry and Applying Chemical Ideas. This is video number 8 and we're looking here at UV-vis spectrophotometry. This is part of our analysis of inorganic ions, that is coloured species and or metal ions in aqueous solution. However, the use of UV-vis spectrophotometry can also be applied to organic compounds. And whilst we've set this in the context of the inorganic section, we'll just briefly mention some of the relationships between this sort of spectrophotometry technique and how it can be applied both for metal ions and also for organic compounds. So, spectroscopy is one of these areas we're going to be looking at in a little bit of detail in this final module. So, a little bit of background may be helpful for you at this stage. Spectroscopy is the study of the interaction between electromagnetic radiation and matter. And so, when it's vaporized, when it is turned into the gas phase, different elements will absorb light of different frequencies. And we've looked at this before in things like flame tests, and we've also applied this in colorimetry. So this is nothing new. This is something that we've been looking at before. And what we want to do now is focus in on specifically what's happening with these absorption bands. So the absorption bands are created when particular frequencies or wavelengths of electromagnetic radiation are absorbed by a particular part of an atom or molecule. Now it can happen in different places, and of course it can happen multiple times for the same atom or molecule, and therefore we may get a series of bands that are being produced as a result. The amount of energy that's required for electrons to move from one energy level to another, or from one subshell to another, varies depending on how far apart those two are. And so therefore, because the energy corresponds to a certain wavelength of light, so the amount of energy required for electrons to move from one subshell to another can differ depending on where they are and where they're going to. What we do, which is something that we did when we were looking at colorimetry, for example, is we compare the intensity of the absorption to a baseline. Then we carry out a series of tests with different known concentrations of our desired ion, and we produce a calibration curve. That then means that any unknown solutions can then have their absorbance measured, and they can be compared to the calibration curve in order to interpolate their actual concentration. So just a quick simplified kind of a diagram of the sort of thing that you see happening when we're using a source of electromagnetic radiation in a sample, and sometimes you might find there is also a comparison or baseline sample. And it may be that this contains something like distilled water, which we would assume is going to absorb little. That's not always the case because of water molecules being present. But if we make a comparison, then what we can do is we can look at what the difference is as a result of the passing of that particular type of electromagnetic radiation through the sample. What we will need is some sort of dispersing device or monochromator that's going to remove all of the other wavelengths of light that we're not interested in and just channel in through some sort of a prism and slit the specific wavelength or wavelengths of light that we're interested in measuring. From this we can produce an absorbance graph, and you can see from the graph here that one of the interesting things is that we've got a trough rather than a peak, and this is one of the things that sometimes can manifest itself in some of our spectroscopic analyses, as these are representative of the levels of absorbance. So obviously if the particular wavelength of light passes straight through the sample, nothing will be absorbed and 100% will go through. If 50% of that was absorbed, then we would find a little trough, a little dip occurring, and it would turn at that 50% mark. So this just gives you a bit of an idea about the types of outputs we get, and again try and draw the comparisons between this principle of UV-vis and what we've seen so far with spectroscopy in terms of the applications of flame tests and colorimetry. It's all the same, it's just different wavelengths of light are being absorbed and are therefore exciting electrons, and sometimes those wavelengths are within the visible spectrum, which means that when the light is emitted we can see it as a color, or they are beyond the visible spectrum into the UV, and therefore they won't have a color. So looking specifically then at UV-vis, we are talking about energy transitions for the ultraviolet range of around 200 to 380 nanometers, and then from about 4 to 700 in the visible range. And that's obviously going from violet through to red. So sometimes we will be able to see the effects of this sort of spectroscopy simply in looking at the color of the solutions, and as we've talked about before, the color of the flames. But sometimes the absorbance will happen in the ultraviolet, and so therefore we'll need a different type of detector in order to determine what's actually going on. As we mentioned, we need to produce a calibration curve. The calibration curve is very important because it allows us to be able to interpolate information on the basis of a series of data points that come from the construction or the production of known concentrations of solutions, standardized solutions, and their measuring of their absorbance. And of course that means that if we use an unknown, we can therefore interpolate from our graph the absorbance versus the concentration. Now this linear relationship represents what's known as the Beer-Lambert law. If the Beer-Lambert law is being obeyed, then we have a direct constant of proportionality that links our absorbance to our concentration. And you can see the Beer-Lambert law is actually expressed by this mathematical expression here, which you may find on your data sheet, so you just need to be aware of each of these things. A is obviously the absorbance. Then we've got this little Greek epsilon, and it stands for the molar extinction. I'll say nothing more about that other than the fact that the molar extinction has a different numerical value depending on the particular solution, so the particular substance you're looking at, and for a particular wavelength. So each of these two things is going to be related. L is our optical path length. And that's going to depend on our container. So often we use cuvettes. We probably use those. We use those in colorimetry. You may have as well. And so that's also going to be fixed. So if these two things are constant for a particular value, then what they will do is substitute out of this equation as constants of proportionality, and therefore we know that there is a direct linear relationship between the absorbance and the concentration. The relationship between the baseline intensity of light and the intensity that passes through is also directly related to the absorbance. It's related on a logarithmic scale, and so these are all the calculations that are actually carried out within the devices that we use, so we don't have to do these ourselves. I guess it's possible that you could be given some information in a question that allows you to calculate these things, but if so, you just have to draw out these variables and substitute them into an equation mathematically, as you would have done plenty of times before. It is possible that at certain concentrations the graph will no longer follow the Beer-Lambert law and perhaps will curve away and so therefore no longer be linear. And this is one of the important reasons why we try and avoid extrapolating from our calibration curves. It's very important that you try and make sure that the absorbance and hence the concentration that you're looking for an unknown is actually sitting within the range of values that you've been looking at and not outside. In practice, there are a couple of applications that we might find to UV-vis, and one of these is where we have, for example, two ions in solution. So in this case we've got chromium ions, Cr3+, and cobalt ions, CO2+. If they're both in a solution, if we know that we only have chromium ions, obviously it's very easy. We can just look at where these peaks are and have a look at how we might go about setting up our instruments in order to measure the absorbance at these particular wavelengths. The problem that we have, of course, is if we have more than one ion in a solution, then these results can start to become a little bit skewed because we are having some of that wavelength of light being absorbed by the non-desired ion. So, for example, at this point of 400 nanometers, where we've looked at for chromium, you can see a small amount of the cobalt will also be absorbing the light of that particular wavelength as well. Now, the fact that the value is so close to zero suggests to us that that's not really going to interrupt the accuracy of our results for the chromium ions. Notice though that if we're trying to measure the absorbance of cobalt, that the higher level of absorbance of chromium is going to create a bit of a problem. In fact, trying to find the point which is probably somewhere between here and here, which is the lowest absorbance levels for the chromium and the highest levels of absorbance for the cobalt, is what we're trying to look at. So this is why you need to analyze these kinds of spectra to get a sense of which types of wavelengths of light are going to be most likely to be absorbed, and for mixtures that contain multiple ions, what you might need to set your desired wavelength at in order to get the most accurate results that you can, and therefore have absorbances that are going to be linked most directly to one of these ions and not have results affected by one of the others. And just a final word here, this is the table that is in your data sheets. So these are obviously relating to organic and not inorganic substances. And you can see that we have some values present for wavelengths of electromagnetic radiation that corresponds to these different types of substances. And you can see that, as we've talked about before, primarily what we're looking for are pi bonds, which are present in double or triple bonds, or we're looking for lone pairs of electrons, unbonded electrons, and they're most commonly found on oxygen, nitrogen, and also on the halogens. We may have some additional data that's there. I think at this point in time, I wouldn't be worrying too much about going too deeply into the chemistry, or really the physics associated with what's happening with these electrons and their interaction between electromagnetic radiation. But do make sure that you can look at these peaks and get a sense of where you think the type of bond or the type of functional group is that's indicated by UV-vis spectrophotometry. Thanks for watching.